All right, so we're going to talk about heat capacity and connect with what we did in lab yesterday. I had you guys, it's weird, I had you on Wednesday first semester, now I have you on Thursday, right? All right, so, I'm kind of stuck back here. A quick note about the way we use words. In the old days, people thought when you put a pan of water on the stove and you turn the stove on, the stove actually added something to the pan of water. And the stuff they thought it was adding, they called caloric. And if you had a piece of copper and you made it hot by putting it in a fire, it added caloric. And caloric is what made it bigger. Later on, when we were able to measure things very carefully, we realized that the mass of the water or the mass of the copper didn't change a bit. When they got hotter, it was the exact same amount of matter. So something was going on with the matter itself. We weren't adding something. But historically, we call the energy, the thing we add to water or anything to make it hotter, we called it caloric, or we measured in calories, and that's kind of where the word comes from. Okay? So just a little fun fact there. What we're going to do is talk about heat today. And so heat is the energy we transfer into a system that changes the thermal energy of the system. So imagine you go outside this morning while you were waiting for your call about the 2-hour delay, which never came, right? That was a bummer. And you find a baseball in your front yard. You pick up the frozen baseball and you hold it in your hands. Are you going to warm up the baseball? Yeah. Are you adding energy to the baseball? You are. You're adding energy. It's coming from your hands. You're making it warmer, right? So the energy you're adding to the baseball is changing the temperature of the baseball. So we would say the energy you're adding is called heat. If you took the baseball and you chucked it, would you be adding energy to the baseball? You would. Would that be would throwing it though make the baseball warmer? No, it would make it move. So we would not say you are adding heat to the baseball. So heat is a very specific word. It means the energy we add that makes something warmer. Okay, does that make sense? I can take a baseball and I can put it on a shelf. I would be adding gravitational potential energy. Now it's got more potential energy than it had before. I added energy to it, but that energy didn't make it warmer. So we wouldn't call it heat. We would call it work. Okay? So that's the difference. That's how we use the word. So heat is very specifically energy that makes something warmer. You can transfer energy to things that doesn't make them warmer, like throwing a baseball. We're going to use the variable Q to represent this heat. So we do this in labs, that's not a surprise. We're just running out of variables. We can't use H. H is reserved for enthalpy from chemistry, if you've had chemistry. And in physics we use H for the height of something. So we're just going to use Q. And we're going to say that Q is positive, it's greater than 0, when we add energy to a system. And Q is negative when we take energy away from the system. All right, that's just going to be our sign convention. All right, so in lab, we asked, how does the change in temperature depend on the energy we add? And you got a straight line. And I think what everybody said was that the energy, the temperature change was proportional to the energy we added. You had twice as much energy, the temperature went up twice as much. It was proportional, okay? We also found that the change in temperature was inversely proportional to the mass. As the mass got bigger, the change in temperature got smaller. And as the mass got small, the change in temperature got big, right? Microwaving a cup for 30 seconds makes it pretty warm. Microwaving a whole bucket of water for 30 seconds won't change its temperature very much, right? If the mass is big, the change in temperature is small. So we got these two things from lab. And a mathematician would write it in notation, which means the change in temperature is proportional to Q, and the change in temperature is inversely proportional to M, or proportional to 1 over M. Okay? By the way, on your conclusions in lab, guys, you can't say the change in temperature is inversely proportional to 1 over M. You got to do one or the other. It's proportional to 1 over M, or it's inversely proportional to M. It's a double negative to say it's inversely proportional to 1 over. That's just saying they're directly proportional. Okay? All right, so that's what we know so far. So now let's do a thought experiment. You guys have a minivan in your life somewhere, sometime in the past? Most people have been in a minivan, in a carpool or something. A minivan's got a tank that's about 20 gallons, okay? If you know somebody with a big, huge truck, though, maybe they have a big, high-capacity 60-gallon tank. So here's a thought experiment I want to do, okay? If I have a 20-gallon tank and a 60-gallon tank, which tank would you say has the greater capacity? The 60-gallon or the 20-gallon? Which one? Point. Because they're all pointing that way? Yeah, that's right. 60 gallons of bigger capacity. Okay. Now, what if I add 12 gallons to each? What if both vehicles pull into the gas station on complete empty? And I put 12 gallons in each one. What's going to happen to the fuel gauge on this guy? If I add 12 gallons to a 20-gallon tank, and it's on empty, how high is it going to go?
Over half.
Over half? How far over? Yeah, could you tell me what percentage? 60%. It'll go to 60%, right? The exact same amount of gas, 12 gallons, goes into a 60-gallon tank. What does the gauge do? Goes to 20%. 12 out of 60 is 20%, right? So, the same amount of gas had different effects on the gas gauge, right? The car that had the large capacity had a small change in the fuel gauge. And the car that had a small capacity had a large change in the fuel gauge, right? And if you drive a Honda Civic and it only has a 12-gallon tank, 12 gallons will take it all the way to full, right? Okay, so I think it makes sense that the capacity of a tank and the amount of the change are inversely proportional. Does that make sense kind of to you? How much your gas gauge changes is inversely proportional to the capacity of your tank. All right? Now, the reason that's a good analogy is because all substances can store heat, but not all substances have the same capacity to store heat. Some things can hold a lot of heat. Some things don't hold very much heat at all. What do you think holds a lot of heat? What substance? Take a guess.
Metals.
Pick one.
Steel.
Steel. Think it holds a lot of heat?
Yes.
It actually doesn't. I'll come back to that, okay? People think that the last three classes all said gold. I don't know why. Everybody's got gold laying around, doing experiments. Some things, like water, are great at storing energy. Water is about the best you can get. It is incredible capacity for storing heat. It can store lots of thermal energy in there, okay? So, if you had a fixed amount of heat, the temperature change will be a small change. If you have a large capacity, then adding energy, it'll make a small change in the temperature, okay? So this is part 3 of our lab. So a couple of you made some fancy graphs and you even color-coded it for me. So I snagged somebody's, I forget who. Maybe Toby's. No, it's not you. Let's look at what happens if I add 30,000 joules of energy to water and oil. If I add 30,000 joules of energy to water, how much does the temperature go up?
20 degrees Celsius.
Yeah, slightly less, maybe 18, right? You guys see that? Now, I'm going to add the exact same amount of heat, 30,000 joules. And I'm going to add it to the exact same amount of matter, 0.4 kilograms of oil. It's the same amount of matter. But what happens to the temperature change?
It's 40, not that.
It's like 45, right? It's double. So what does that tell you about the capacity of oil to hold heat? It's bigger or smaller than water? It's smaller. The smaller the capacity, the bigger the change in the temperature. So water has a huge capacity to hold heat. Adding 30,000 joules only warms it up 18 degrees. But the same amount of energy added to oil warms it up 45 degrees. So it must have a smaller capacity to hold energy, okay? So the capacity of something to hold energy depends on the molecular nature. But the big picture is, if you have a small capacity, you get a big change in temperature. And if you have a big capacity, see the big letters? You get a small change in temperature. They're inversely related. Okay? So mathematically, I would say that the change in temperature is inversely related to the capacity. Okay? Does all that make sort of sense? If you don't get it all, it's okay. I'm trying to motivate where the equation comes from. So this is kind of background. I don't really like equation dumps. When you walk into class, the teacher says, here's an equation, solve problems with it. It's not that hard to figure out kind of thought experiments that help you see why it's that way. So that's kind of what we're doing. All right, so heat capacities are just listed in a table. And you guys have seen this table probably when you clicked on the link in the warm-up or yesterday in the homework, right? There's another table besides the linear expansion coefficients that's called heat capacities. And it just tells you the heat capacity. Now, it uses a bit of a goofy unit. It tells you how many joules of energy it takes to make 1 kilogram get 1 degree Celsius warmer. Okay, that's how we measure the heat capacity. So what do you think on there is the best? Look at the numbers. Jacob, what do you think?
Water.
Water. Is it close?
No, not really.
There's nothing that's even close, right? There's not even anything that's even half. Barely. Okay? Water is a rock star for holding heat. If you want to hold a lot of heat, you want water. Okay? Where's steel on that list? Or gold or copper? So steel is basically iron. It's 400. It's less than 1/10 the capacity of water. So steel is not very good at storing energy. Okay? It's good at something else, but it's not good at storing it. Did you?
Why is water's other forms not good at storing energy?
Oh, yeah, so, give me a minute to come to that, okay? So let's just talk about this number for water really quickly. Have you guys seen that number before? Flip back in your toolbox to the handy conversions page. And I'm going to print more toolboxes. Stephen was just in here this morning, actually, when you guys were doing your warm-up, trying to install the printers. My computer forgot how to print over Christmas break, and I haven't been able to print since.
That's joules to calories.
What?
Joules to calories.
We used that back in Unit 3 when we're talking about Twix bars and how much energy you get from them, right? This number you've seen before. 4,186 joules is the energy it takes to make 1 kilogram of water 1 degree Celsius warmer. So a kilogram of water is a liter. So you guys know what a 2-liter bottle is, right? Half of one of those is a liter of water. If I took that much water, that's 1 kilogram, and I made it 1 degree Celsius warmer, so that's like 2 degrees Fahrenheit, 1.8 degree Fahrenheit. The amount of energy I would have to add to do that, that is 4,186 joules, which is the definition of a calorie. That's how we defined a calorie back when we started doing this. We said a calorie is however much heat you've got to add to water to make a kilogram 1 degree warmer Celsius. Okay? So you've seen this number before. Okay? It's the conversion between calories and joules. So that's defined as a calorie. Now, this is a calorie with a capital C. Calories are confusing boogers, and we're not going to deal with the other one. But here's the short story. If you're in chemistry, you may know that there's also a calorie with a little c. Calorie with a big C is how much energy it takes to make 1 kilogram warmer. Calorie with a little c is how much energy it takes to make 1 gram of water 1 degree warmer. What a pain. We are not going to use this at all in physics. Okay? We just think chemists are goofy to even mess with it. Just pick one of the 2 definitions and run with it. So we're going to use calories. This calorie with a capital C is the same calorie that we use for food. Okay? So when you talk about a Twix bar being 250 calories, that's this calorie here. So we're going to ignore this one, okay? So don't worry about it ever. All right, a couple of notes. The heat capacity depends on the phase of the substance. How much capacity it has to hold heat depends on whether it's a solid, liquid, or gas. Okay? Turns out liquids can hold the most energy because they can move in the most ways. Water molecules can spin, they can jiggle against their neighbors, and they can move through the liquid. They can move many different ways. They can hold lots of energy, microscopic kinetic energy. When you freeze water, it gets locked in by its neighbors, and it can't move anymore, and it can't spin. All it can do is wiggle. So it's not as good at holding heat because there's not as many places for it to go, the kinetic energy. When it turns into a gas, it can move all around and it can spin, but it can't jiggle with its neighbors anymore because it's too far away from them. So it's actually less able to hold heat. Metals are solids. They're locked into their neighbors, and they're pretty stiff, so they can't even jiggle that much. So they're terrible at holding heat. What is a metal good at? It can't hold a lot of heat, but it can conduct it. Okay? So there's a difference between conduction and capacity. Capacity is how much heat it can hold. Conduction is how fast it can send it along. Right? A Lamborghini has zero capacity. Right? Did you guys see the Super Bowl ad a couple years ago? The girl comes out of the airport from Europe to visit her boyfriend. She's got this huge suitcase, and he pulls up in a Lamborghini, and he pushes his button, and this little tiny trunk opens, it's like this big. She's standing there with her suitcase. Then some dude pulls up in whatever they're advertising, SUV, and she puts it in his car, and they leave. A Lamborghini has no capacity to hold luggage, but whatever's in it, it can sure transport fast, right? Metals are good at transporting heat, conducting it. They're terrible at holding it. They have no capacity. Okay? What's the worst thing on that list? Lead. And gold is a close second, right? Look, that's 129, 128. That is like a 40th of what water can do for the same amount of matter. Okay? So metals are terribly bad at holding heat. Water's the best we got. If you remember from chemistry, if you're dealing with gases, you got to worry about the pressure, and that's just one more step of confusion that we're not going to add, so we're just going to ignore gases, okay? Because with gases, the heat capacity also depends on the pressure. That gets even more confusing. So here we go. This is what we know. The change in temperature is proportional to the energy we add. It's inversely proportional to the mass, and it's inversely proportional to the capacity. I think I've motivated between lab and our little thought experiment, those should kind of make sense. We can put that all together in an equation. We can say the change in temperature is proportional to Q. Q's in the numerator, right? It's inversely proportional to the mass, and it's inversely proportional to the heat capacity. So that's kind of the equation that's going to put it all together. Now, that's not what's in your toolbox, though. This is the proper way to write the equation. This is the dependent variable. How much the temperature changes depends on the mass, the heat capacity, and the heat we add. But we usually rewrite it. We put those two things up here. Multiply both things, both M and C, to get rid of the denominator. And when you rewrite it, it looks like this. It's the same equation. It just doesn't have a fraction, which apparently people like better. Okay? So, I think you've seen that in chemistry. MCAT, right? It's the same idea. We're just talking about it in the context of energy now. The heat it takes, the energy we got to add, is equal to the mass times the capacity times the change in temperature. All right? Do I have this in your toolbox, the plus and minus? Yeah, so if you gain energy, make Q positive. If you lose energy, make Q negative. That won't snag you up too much on the homework right now, because if you get the wrong answer, it tells you, think about the sign, right? You get the little wide-eyed emoji. All right, let's solve an example problem. I want to make some tea. I've got 1 cup of water. This is about 240 grams worth of water. That's what it'll hold. The water starts at room temperature, so the water out of the faucet's about 20 degrees Celsius. And to make the perfect cup of tea, I just need it slightly below the boiling point. So I'm going to do it 95 degrees Celsius. How much energy do I have to add to a cup of water to get it to warm up to 95 degrees Celsius? That's what I want to calculate. Okay? So, to calculate it, we got to find water on the table. It's not that hard. Just find water. It's not ice. It's not steam. It's just liquid. We're going to make a diagram, and this is the small tweak. You can make teapots. You can make cute little smiley faces on your teapots, tea bags, steam, whatever. But the diagram that I care about, and you need to count for me, is a graph. And the reason we do this is because we are going to keep using this graph as we get more complex. When we add energy and we lose energy at the same time, we're going to draw them all in the same graph. So for the rest of our unit, our diagrams are going to do a sketch of the temperature versus heat graph, okay? Now, today, you've only got 2 options. Either this stuff warms up and the graph goes that way, or you cool something down. And which way does the graph go? That way? No, it can't go that way. Going that way means as you add energy, the temperature gets lower. It goes that way. Okay? So if you gain energy, draw an arrow that way. If you lose energy, draw an arrow that way. Okay? That's all we're going to do today. We'll make our diagrams more complicated as we solve more complex problems. Okay? All right. Here's my variable list. The temperature final, the temperature initial is 20. The mass is 0.24 kilograms. The heat capacity I get off the table, and you always got to keep your units with your numbers. Heat capacity's got a goofy unit. It's joules per kilogram degree Celsius. And then we're trying to find Q. Okay? I'm just going to evaluate Q equals MC delta T. This C, look at the units on it. It's joules per kilogram degree Celsius. What's the unit there? They're going to cancel. What's the unit here? What's T final minus T initial? That's going to be in?
Celsius.
Celsius, that's going to cancel. If that cancels and that cancels, what's left?
Joules.
Joules. Okay? You know you're doing it right when all your units cancel. That's why it's handy to keep your units with your numbers. If you ended up having Fahrenheit here and C there, you know it won't cancel. You can fix it before you get the red X and have to start over. Right? So keep track of your units. And then I plug in my numbers, I get 75,000. Does anybody have a sense whether that's reasonable or not? 75,000 joules seem reasonable? You actually know how to do this. How much energy does a microwave add every second? About 1,000 joules. So if the microwave adds 1,000 joules every second, how long would I need to add 75,000 joules? 75 seconds. Is it reasonable that it takes 75 seconds to warm a cup of water? From your experience. Does anybody have a microwave at home that does it in 18 minutes?
No.
Probably not.
I think if my microwave does it in 30.
Does anybody's microwave do it in 2 seconds? Not any microwave you have at home,
No.
right? 30 seconds?
Yeah, we can change the settings of how many. energy
Whoa,
we use to the-
that's a pretty fast microwave.
My dad spent a lot of money on it.
Yeah. It's got a 2,000 watt microwave. That might be illegal, I don't know. It's probably not. So you guys can actually, you can tell that's a reasonable answer. 75 seconds is ballpark correct, right? Okay, couple notes. This thing up here tells you what units to solve the problem in. If you want to go hunt around, you can find tables that have the heat capacity in calories per pound degree Fahrenheit. You can find them, and you can use them. But it's a whole lot easier just to use the one I've got for you, okay? So if you get a problem and your temperatures are in Fahrenheit, convert it to Celsius. If your masses are not in kilograms, convert them to kilograms. If your energies are not in joules, convert them to joules, okay? You have this conversion in your toolbox, but you might want to put it on Unit 7's page. So if you do, go ahead. Because we're going to use it a lot in this unit. We speak calories. You have no idea if I gave you a donut that was 100,000 joules of energy. Is that a lot? If I gave you a donut that was 1,000 calories, is that a lot? Yeah, that's half your daily allowance in one donut. We speak calories, we know calories. So we often convert things to calories or are given things in calories in problems. So having this conversion handy is useful. So write it on your Unit 7 page if you want. All right, we have 20 whole minutes to solve the problems, and I got some bad news for you guys. I feel bad. Some of you guys are just going to feel cheated, but this is a really easy problem set. So I'm sorry. I know you're disappointed. I'll try to make it up to you next week. But for now, just crush them. There's 10. They're all straightforward. Even the challenge problem isn't really a challenge problem. It's a micro challenge problem. It's a tiny challenge. And I bet you could knock out most of them in 20 minutes if you got on it. So actually, you guys have 25 minutes to go lunch. So go ahead and get those going. We'll do a lab on Monday and we'll do new stuff on Tuesday, so you should have these done by Tuesday. For planning purposes. All right? Annie? Did you forget our deal?